rebound by Peyton Crispin. He's going to put it back. And he got it! The Lakers hit a three.
Welcome back again. He's a court on your SWOCC Lakers.
Can't get the shot to go, and the Lakers win the ball game.
Goal! Lakers win! Lakers win in overtime. 108-106.
Do you like to work with metal, fire, electricity? Would you like to make money doing it? At Southwestern, we can help make your dream a reality. With our degree and certificate programs in welding, you'll be prepared for a career in the welding and fabrication industry in as little as a year. Check out our website and let Southwestern spark your career in welding today.
Southwestern Oregon Community College gave me the opportunity for a new career doing something I love. I'm Amber Yardley, and 3 years ago, I knew I needed to make a career change for myself and my family. With the support of staff, my academic advisor, and the instructors at SWOCC, I now have a dream job and the confidence to continue my education. Contact Southwestern Oregon Community College and start the journey to your new career today.
This is Southwestern's Dental Assisting Program. In just one short year, you could be a dental assistant. Sign up now for your one-year dental assisting certification.
Hello, my name is Crystal Hopper, and I am the assistant to Dr. Erin Coiner, who you guys will be hearing here shortly. Thank you, everyone, for coming out tonight. I hope that you were able to sign in at the front when you came in. If not, you can sign in whenever you leave, please. It just helps us with letting the school and everybody know how many people attend this program. And I wanted to go ahead and introduce Dr. Coiner now. He is the professor of physics and over the engineering and physics department here at SWOCC. He's also the local representative for the Oregon NASA Space Grant Consortium. He is also our NASA JPL Solar System Ambassador and the faculty rep for Invent Oregon. We've got some exciting things that I was going to tell you a little bit more about a little bit later, but if just everybody will help me welcome Dr. Coiner.
Well, thank you guys, and thank you, Crystal, for that introduction. Welcome to everybody, and thanks for attending. Today we're going to talk about the active sun, flares, CMEs, and space weather, and its impacts here on Earth. For those of you that know me well, the original working title of this talk was "Watch Out, Radioactive Man, the Sun is Exploding Again," a direct reference to The Simpsons, but that's just the nature of my being. The reason why we're talking about the sun, in part, is because that happens to be my cup of tea from a physics perspective. I came to SWOCC after spending a little bit of time as a postdoc at NASA Goddard, and then spending some time as an adjunct spending a little bit of time as an adjunct teaching in Oklahoma. But before I was actually teaching, I was a research assistant and a research postdoc at NASA Goddard, where I did a lot of solar analysis of coronal heating. And then before that, when I was in grad school, I was doing analysis of solar flares and CMEs at Rice University. So the sun is kind of my main topic of interest, and it's an interesting topic for a lot of reasons, because our sun gives us all the light and all of the energy that we actually need as a planet, but it also tends to be a little bit temperamental. We'll talk a little bit about those temper tantrums from time to time. The slight problem with having your entire planet, your entire solar system powered by a giant nuclear furnace is occasionally it decides to behave like a 2-year-old. And when it does that, it tends to throw very energetic particles at us from any number of different directions, and those energetic particles can interact with things that we have floating in space, like our countless numbers of satellites. Any of the electronics on board the satellites can be affected by solar energetic particles. Any astronauts we have in space on missions can be affected and be subject to radiation doses due to energetic particles from the sun. If the energetic particles reach ground level, they've shown on a number of events that they can actually create things like power blackouts and also radio signal interference. And so there are lots of reasons, aside from the fact that anything space-related is cool, and looking at things, and of course, doing any kind of a solar talk means I get to do an obligatory Aurora Borealis picture. I still can't say that phrase. I always used to be able to, but it always happens when I get nervous. But we'll get into the actual talk. And I have to give you a little bit of perspective. Those of you that have been in my class before, you realize the perspective part is usually the scary part. But I have to give you a little bit of perspective. That's the sun. That blue dot up there that you can barely see is us, all of us. The sun being very large. In fact, you can actually put 109 Earths across the diameter, and you can fit 1.3 million Earths inside the volume of the sun. So as Carl Sagan once said, we are in fact a pale blue dot. And the sun is very much gigantic, and no, even though my Q&A helper Wade would want me to do this, I did not include the They Might Be Giants song, but there is a quality They Might Be Giants song that covers a few of these things. The sun is interesting in the sense that it has no solid surface. It has many layers, and they're very turbulent, and there's active motion throughout. But all of the layers rotate at different speeds depending on their latitude. So things get fairly twisted compared to what we would expect from rigid body rotation. And no, for those of you in my physics class, that was not designed to create flashbacks to this last week's lecture. We'll wait for a second. This is actually a video from one of my former colleagues, Dusan Ostersill, who used to work at Goddard, now he works at George Mason. Is there a trick to getting the videos to play? So what the sun looks like, in visible light, you see it as the nice yellow dot or the nice white dot, because we don't ever look at the sun in visible light because it tends to hurt your eyes, but as you look at it in different wavelengths, things get very interesting. This is an example. This is from April of 2002. This was one of the big X-class flare events during solar cycle 22, in which case we had a lot of energetic particles. All of those white dots that you see in the in the coronagraph are all supercharged electrons, and we're seeing them through Thomson scattering at the coronagraph. And all of those are headed toward Earth, and they happen to be picked up by a detector on the SOHO spacecraft. As you zoom in, as it zoomed in, you also saw it in green. You see the ultraviolet. We do a lot of observations of the sun in extreme ultraviolet, and we look at the corona. That's typically plasma that's around 1 million to 2 million degrees, which might be interesting to some of you because the corona is the furthest away layer of the solar atmosphere, yet it's 1 million to 2 million degrees. But the actual photospheric surface is only about 5,780 degrees. So one of the outstanding questions in solar physics is, how did the corona, which is decidedly less dense than the actual surface of the sun and much further away from the actual power source, how does it get to be multiple orders of magnitude hotter than the rest of, than the actual surface of the sun? And we'll talk a little bit about that because the new mission, Parker Solar Probe, has given us some insight onto that, and the joys of having formerly worked at one of the institutions that is a PI on Parker Solar Probe is you actually get to find out stuff. A little bit more, the sun, as I said, is multi-layered. It has 3 main layers on its interior, and then it has 3 main layers that behave sort of as an atmosphere. If you can consider a giant ball of plasma something that has an atmosphere, you have the core, you have the radiative and convective zones that are actually internal to the photospheric surface. That's sort of, if you think about a geology lecture, the photosphere is basically the visible surface, and anything below that is essentially like the mantle for the sun. Whereas anything above it, the chromosphere and the corona, and there's a little band between the chromosphere and the corona, which we call the transition region, that makes some very interesting pieces of the solar atmosphere. Observing things in all of the different wavelengths and at all of those different levels, we see different levels of activity depending on what's going on. The sun is the most observed object in all of astronomy, and there's a very good reason why. All of these satellites that are currently up, this is the current fleet of NASA and NASA-adjacent projects. Some of them are actually led by ESA, which is the European Space Agency, but NASA helps out with them. The ones in boxes I have connections to. The one in the red box, RESI, is actually an X-ray observer. It's now been decommissioned because it finally stopped collecting data, but that was part of my master's and my PhD thesis, was looking at the effects of, or looking at observational constraints created by RESI data. So I always mention that one. SOHO is our Solar and Heliospheric Observatory. It's been out at the L1 point for almost 30 years now, and it continues to take constant view of the sun in multiple wavelengths. So we see a lot of ultraviolet. We see some white light images. We also see magnetograms, so that we can actually keep an idea on how the solar magnetic field is behaving, and that's important, and we'll get to that later. So when we look at things in visible light, like I said, the sun looks fairly plain. It's typically white or yellow depending on what filter you're using. If you're using an H-alpha filter, it appears red, but that's because that's the red end of the visible spectrum. And it's typically fairly bland. It has some dark spots. Those are actually sunspots. And believe it or not, those sunspots are actually the cool parts of the sun, not from the excitement perspective, but they're typically about 2,000 degrees cooler than the surrounding plasma, so that's why they actually appear dark. And they exist because those are pockets of the sun that the magnetic field is particularly strong in. So typically when we see sunspots, we see groups of sunspots, they become known as what's known as an active region. And as you might guess with the title like active regions are the locations where solar activity like flares and CMEs are most likely to generate. But aside from visible light, we can look at the sun in any number of different wavelengths. And we do through a telescope called SDO, or the Solar Dynamics Observatory. We're looking at the Dopplergram, which is actually a measurement of the magnetic field, and looking at velocities as the magnetic field escapes. We've got the HMI magnetogram, which is looks at Zeeman splitting of atoms and determines whether the magnetic field is coming in or out of the sun. The continuum image is white light. It's basically like if we took a camera and actually pointed it at the sun and the camera didn't melt. The 1700 and 1600 and 4500 images are of the photosphere. Those are specific wavelengths within the ultraviolet continuum, or within the low ultraviolet. And then you get into 304 is a helium line. And then all of the ones, 171, 193, those are all very excited states of iron. And they're typically looking at the upper corona and the transition region at about 600,000 to 1 million degrees Kelvin to up to 2 million degrees Kelvin if we look in the right places. And if you look at the 131 angstrom line, you're looking specifically at flaring regions, and we're seeing plasma that radiates in that line that's plasma at about 10 million degrees. So this is all plasma that's very hot. It's mostly protons because the energy is such that the electrons have all been stripped away, so we're dealing with plasma, we're dealing mostly with protons. We have some heavy ions in terms of some helium nuclei and alpha particles, and some you can have heavier element species all the way up through iron. Stars don't like anything usually above iron, at least in terms of their natural processes. Everything else happens after iron when things go wrong, because once fusion up to iron is possible. After iron, it costs more energy to fuse things than you actually get out of it. So the nuclear furnace stops working. And unfortunately, the nuclear furnace stops working, but then gravity, which is always present, does not. So once you no longer have the furnace to blow everything out, gravity decides to crush everything, and we end up with wonderful things called supernova. Our sun is not large enough to actually go supernova, so we'll see it go through like a nova phase when it gets old enough to do so. It's still in midlife crisis at the moment. It hasn't decided to do anything too irrational yet. So why do we care about solar activity? Well, there are points when the sun is particularly active, and it follows an 11-year cycle, roughly 11 years. Sometimes it's 12, but and you can see here this is an example of 3 solar cycles, the last 3. We're currently at the bottom of solar cycle 24. This is actually good for now, but that means for someone like me that's a solar physicist by trade, this actually means that this gets to be kind of my downtime, because the sun's not really going to do a whole lot, but it's a good time to send out missions like Parker Solar Probe and the Solar Orbiter, which will actually launch in February, and we'll have time to get them into the right places before most of the fireworks happen. And you actually find out that even in the quiet times, you learn a lot of stuff about the science that we didn't understand, and we'll talk about specific results. So why does the cycle happen? Well, remember what I said about the sun is not a solid ball. It actually rotates at different speeds depending on where it is from a latitude perspective. So it rotates faster at the equator than it does at the poles. Well, if I have a magnetic field, and you can kind of do this at home if you've got a bar magnet or a refrigerator magnet, you can actually set the bar magnet on the table, and you can set a piece of paper over it, and you can actually see kind of the lines of force of the magnet. If you've got something like iron filings or dirt or something else, you can actually trace out the magnetic field. Well, if I have a magnetic field that's just a magnet that's just straight up and down, it's going to have a field similar to what the sun does if we didn't have rotation in it. And it would just be straight up, and it would be straight up toward North Pole, straight down toward the South Pole, and then you'd have field lines that come out of either side, and then they wrap around. The problem happens that, as we said, the middle is rotating faster than the top and bottom of the thing, so the field lines start to get warped. So instead of being straight up and down, by the time you get to the solar maximum point, the field lines have been bent so that they're essentially toroidal around the equator of the sun, and that actually causes most of the activity to happen in active regions around the equator. And then as we get down from solar maximum, it continues to spin around and eventually straightens itself back out. But by the time it straightened itself back out again, what was the North Pole is now the South Pole. So it flips every 11 years. And then it goes through another cycle, and it flips itself back. So there's two different solar cycles. There's one that's about every 11 years that goes from solar minimum to solar maximum and then back to solar minimum. And then there's an overarching one that's about 22 years that's essentially two of those cycles, but it's the amount of time it takes for it to start at North Pole and then go back to that same magnetic configuration where North Pole was back at the top again. There we go. And we physicists, and particularly we solar physicists, are extremely brilliant with naming things. I say that in all sarcasm. Not really sure what to call the first time I saw this, I wasn't exactly sure what to call it, and then I realized that apparently all the solar physicists before me had kind of the same view of it as I do. This is called the butterfly diagram. I'll give you about 3 seconds to figure out why. But what this is it's a map of essentially where the active regions are located over the course of time. And as you see a solar cycle going through, you see that they can start, the solar cycle in the active regions can start at about 30 degrees north or 30 degrees south, but over the course of building up to solar maximum, they all get closer and closer to the equator. And then they stop for a while when we get to solar min, and then they resume, and then they create another butterfly every time you go through another cycle. So you can chase these all the way back. This one goes back to 1870. There's actually versions of the butterfly diagram that go all the way back to the Maunder minimum of the 1600s, where we actually went through several decades of not having any sunspots, which was weird. I wasn't alive for that, but I've read a lot of stuff about it, and it was very interesting. And we were kind of worried at the beginning of solar cycle 23, because at the beginning of solar cycle 23, the sun was really quiet for about a year. I had just moved from Houston, and I'd actually gotten to Goddard, and I realized I'd gotten to Goddard at solar minimum, but you never realize just how critical that is until you work in a building that's full of solar physicists that are trying to figure out how they're going to get paid. And so they're trying to figure out, how many proposals do I have to write to explain that the sun hasn't had a sunspot in a year? Luckily, it started behaving again and started giving us things to look at so that my neighbors down the hall were not particularly alarmed as much anymore. So we talk in general about the sun and we talk about activity, but I did specifically mention 3 things in the name of this talk, so I figured I better talk about them. And 2 of them are flares and CMEs. Flares, we've all kind of heard about because people will talk about solar flares, as it were, occasionally. Let me load up another video. These are fun. And if you watch this one, notice that bright glowing area in the center. As it goes around, you'll see it get progressively brighter, and you'll start to see the flare go off. Froze up. It's thinking about it. It's reloading. That's all right. That one's not as much of a fun one, so we'll hop through. This one's more interesting. This is actually, this is one, of course, from our friends at NASA Goddard. I will give them full credit for this, but you'll get to see what an interesting flare looks like. To grow up, but then you see the actual flare go off, and you're starting to see this loop arcade that develops in the UV. We'll talk a minute in the next couple of slides about how that loop arcade comes to be, but what happens is it's an interaction of the magnetic field that we didn't necessarily think was supposed to happen, but we figured out that it can under certain circumstances. And we'll let the coronal rain work because that's actually a cool part. And just to give you an idea, again, there's the blue dot to scale. That's the size of the flare. And this is kind of an average flare. Actually, it's not even a really giant one. I'll go ahead and... Dallas, we can go ahead and skip to the next one. What happens, and I'll point this out with this particular slide, what happens is a phenomenon called magnetic reconnection. And when you look at things, and when we look in the textbook for how magnetic fields are supposed to behave under normal circumstances, there are rules that you're not supposed to be able to cross magnetic field lines. So particles can't cross magnetic field lines, and they basically spin around magnetic field lines, and they don't actually cross between them. But there are points when you can have a magnetic field, if it gets twisted enough, where I can have magnetic fields that are going in opposite directions, and the magnetic field lines actually get close enough that particles can actually diffuse across them. And you're not supposed to be able to do that, but what happens is when you are able to diffuse across, it actually creates the equivalent of an electric short circuit. It releases a lot of electrons in the upper atmosphere of the sun, and they all stream down to the surface because the surface is much more dense. And then as they come down toward the surface, they actually give off X-rays and give off ultraviolet light because they're being slowed down as they're approaching the more dense plasma, and that's what we see in terms of the flares. If you look at this particular diagram, I don't know if the laser pointer's working, but you'll notice the point in the middle. It's conveniently titled the next point because we solar physicists, as I said, are really creative with names. But that X point, what usually happens, the reason I said flares and CMEs and I mixed them together is because in some events you'll actually see the flare go off and you'll see the flare stay on the surface, and then that top half that's up there above the X point will actually blow off and go into space. And when the sun decides to blow something off and send it into space, it's known as a coronal mass ejection because we're ejecting mass from the corona. Again, really creative naming, but it works. And that coronal mass ejections are things that have energetic particles in them. They can be excited iron atoms, excited helium atoms, alpha particles, protons, electrons, any number of species up through iron, and these energetic particles get sent off into interplanetary space into what we call the heliosphere. The heliosphere is a another fancy scientific term for, I'll use a Disney reference. It's essentially the sun is on Pride Rock. Anything I can throw stuff off and hit is within my domain. That is the heliosphere. I would use the actual quote of anything the light touches, but sometimes you can actually see sunlight from outside the heliosphere. So, and here's another more detailed example of a reconnection site. You'll see the energy flows, and watch the video as you look at this, and you can see kind of the same thing. The green and blue that you'll see are actually X-ray emission, and the yellow and the red are actually ultraviolet. So you're seeing a lot of emission in the ultraviolet, and you're seeing a lot of X-ray emission as this is going. You're seeing a loop-top source of X-rays as this flare is going off. So we're seeing the reconnection at the top, and you're seeing the cusp on the way down. You're not necessarily seeing the top half, because at this point the top half is already blown up. It's already blown away. I've gone too far. Nope. And this is a little bit of shameless self-promotion. This is actually from one of my papers. About the time I finished my PhD thesis, this was the last paper that came with my thesis. And what we were looking at is specifically looking at ultraviolet emission compared to where the X-ray emission was. So in that first box, you see ultraviolet emission within a flare, and we have two boxes there, source 1 and source 2. And we're looking at how those sources behave compared to the overall X-ray emission. So I'm comparing it to X-ray emission at 50 to 100 keV, which is fairly energetic hard X-rays. These are all due to electrons that are crashing into the surface of the sun, and they're giving off X-rays as they're being slowed down. Essentially like running things into a brick wall, except they give off X-rays on the way because they're slowing down from such high speeds. If you look at the time series next to it, though, all of those white, the white overlaid contours are all the X-ray emission. So notice one thing about the ultraviolet emission. I have a really bright source that's down there at the bottom that I call source 2. But if I look at where the X-rays are, there's very limited X-ray activity in that particular location. Yet when I look at source 2 from a light curve perspective, the ultraviolet is actually still responding to the hard X-ray emission. Before my paper came out, and before other papers similar to it came out, we always thought that the ultraviolet would respond directly to the hard X-rays, and they would always be right on top of each other from a spatial perspective. Now we're seeing that the ultraviolet can extend much further out along the solar photosphere and the solar chromosphere. And so we actually, instead of having just a series of 2D loops that we would call typically the flare arcade, we can have three-dimensional structures that are known as separatrixes and separatrix surfaces, where I can create a series of X-ray emissions, and those X-ray emissions can connect to various ultraviolet emission and various ultraviolet footpoints on the surface of the sun during the flare. So the flare emission is actually much more spread out than we originally thought. So that was flares. And this is a little bit on coronal mass ejections, and each one of these things that you see in the LASCO coronagraph, we have these instruments called coronagraphs because the only time you can actually see the corona from the surface of the Earth is during an eclipse, and being in the exact right spot to see it during a total eclipse at any time can be rather costly, and they're fairly easy to predict because we know when they are all going to happen, but we'd like to actually be able to observe the corona on days that aren't eclipse days. So we make our own. We send a spacecraft up and we essentially put a lens cap over over a good portion of the actual visible detector that actually blocks out the surface of the sun. And so that ring in the blue and that ring in the red, the white circle actually represents where the surface of the sun is. And once the sun is blocked out, then we can see all the fun stuff that happens on the outside that we can't normally see because, oh yeah, the giant nuclear furnace is working and it doesn't like to share. So this is another one. And one of the things that we've been talking about with CMEs is how exactly do we know that they get started? There's been a lot of debate within the solar community about, is it flux ropes, is it a shear arcade, what is it that actually drives the CME going off? And we actually found through recent observations from Solar Dynamics Observatory, we can actually see the flux ropes emerge. So we've we've settled sort of on a flux rope interpretation that there are flux ropes that emerge out of the sun. Dallas, this is the one that we kind of joined in progress.
On July 19, 2012, a CME erupted in the visible edge, or limb, of the sun. Because it was on the limb, the flux ropes were in profile and particularly visible. Even more important, the flux ropes appeared about 7 hours earlier in the same
So you can see the flux ropes actually develop,
were visible as a line of figure eights.
and then they show up as the figure eights, and then they'll explode off.
This is the first direct evidence that flux ropes formed well before coronal mass ejection. Footage of the CME from the SOHO spacecraft confirmed the presence of the flux ropes.
And then you see the flux ropes as they
By
blow up.
adding footage from the Stereo A spacecraft, which is viewing the sun from an entirely different angle, the researchers were able to create a three-dimensional picture of the flux ropes. For the most part, they followed a classic figure eight pattern previously observed and predicted by solar models. But some of these ropes also had feet which extended farther away than scientists expected. This deviation from the models is interesting and requires further study. Besides showing proof of early flux rope formation, this study also paves the way for future flux rope and CME research by literally finding a new light to observe them. The possibility of using flux rope formation as an Earth warning system for CMEs means that this line of research can have some very practical and far-reaching applications. And it can also help wrap up some of the long-standing mysteries of the sun.
And so when we talk about CMEs, you saw the flux ropes develop, and one of the things the reason we had kind of leaned toward the flux rope interpretation is when you see a CME, you usually see three parts. You see a leading edge, which acts as a bow shock, and actually shock accelerates all of the plasma ahead of it. You have a bit of a cavity, and then you have the core that is the rest of the mass that's being ejected, that ejects out later, and then once all three parts go by, then the sun will return to normal, and you'll see it go back to the typical streamers. So that's all nice, and that's all a lot of cool pictures from space, and that's what most of my talks end up being, but why do we actually care? Well, let's talk about space weather. The sun is shooting these things off on a relatively regular basis. And they are very energetic particles, and as I said, if they come in contact with satellites in the wrong place, they can cause bit flips and actually cause entire satellites to go dark. Human space exploration, aviation, these things are very energetic, and they're giving off high amounts of X-rays and potentially gamma rays worth of radiation that, I don't know, I've seen one too many Marvel movies. Exposure to that many gamma rays, probably not for the best. And so we'd like to know exactly when the sun is going to throw a tantrum, but like with any like with any situation of that sort, we don't necessarily have all the resources to know exactly when that is. So in order to understand when and how, we sometimes have to actually ask ourselves the question of, first of all, how is it going to do it, and what evidence do we have that it happens? And so that's why we look into space weather. The fun thing about working at NASA, we have a program called Living with a Star, and the program is called Living with a Star because you actually have to go in, and it's very similar to having to learn all of the idiosyncrasies of all of your roommates or all of your family, except now one of your family members is a giant nuclear furnace that likes to throw things at you. And so you're looking at different implications. The cool one, because there's always got to be an obligatory picture in any kind of a solar talk, there has to be an aurora picture, and yes, I included one. It's just not in there yet. But it does affect space travel, and particularly in light of the things that we talked about a couple months ago when Dr. Higginbotham was here to talk about NASA's new Artemis mission to go to the moon and then to Mars. If we're going to put people in space for that long, they have to be prepared for radiation and for bursts from solar activity. So we better actually understand why and hopefully get better at predicting when these things will happen. So what are some of the key solar questions? Well, like I said earlier, coronal heating is a big deal. The corona is between 1 and 2 million on average for the quiet sun, and then it's up to 10 and 20 million during a flare event, but the surface of the sun is only 6,000 degrees. We believe from SDO that a lot of that has to do with like little, what are called spicules of emission, and we also have microflares that happen. Parker Solar Probe indicates that there's solar wind influence, and we'll talk about that in a minute. People more qualified to talk about Parker Solar Probe results gave me results to talk about. And the other thing we want to talk about is solar energetic particles. These are highly energetic particles, electrons, protons, heavy elements like all the way up to iron, accelerated from solar events like flares and CMEs. They can impact communications, they can affect astronaut health. If it's a large enough event, you can actually see a power grid failures. But we have a problem. We can observe certain things at the sun remotely through pictures. And we can observe a lot of things through satellites here at Earth. But there's about 93 million miles in between those 2 points. And there's not a whole lot of coverage in terms of what do these things do from point A to point B. We have them measured at point A, we have them measured at point B, but what exactly they do in between, we're not really sure yet. And that's sort of your lead into the next part. Why does this matter? Well, this is the spider diagram. This is an artist representation, but it's not actually too far off. The orange bubble that's being shot at us from the sun, although not necessarily to scale, represents the solar energetic particles that are being thrown off. And the blue spider around the Earth is actually the Earth's magnetic field. Our magnetic field does a wonderful job of deflecting most of the particles, but if the particles come in too fast, they can actually penetrate the magnetic field and they can actually reach down to the surface of the Earth and start causing fun with atmosphere and with actual surface. And one of the ways that we look at impacts of this is actually an artist representation of a mission that one of my friends is actually on. This is the Magnetic Multiscale mission. It's a series of 4 spacecraft that are orbiting within the Earth's magnetic field and looking for signs of magnetic reconnection caused by solar energetic particles impinging on our magnetic field. Now, I showed you what reconnection does from a sun perspective, that if we get reconnection, we can end up with solar flares. But we also have a magnetic field, and if it ends up with a reconnection, we can have a lot of emission that happens within our atmosphere and various other things. So we look for signs of potential reconnection both on the sun and at the Earth with particle observations. I'm not going to pretend to understand everything that MMS does. If you pick one up on your way out, or if you got one on your way in this morning, you'll notice, or this afternoon or evening, there is a list of our upcoming talks for the Physics and Astronomy lecture series, and one of those, the June 3rd talk, is given by Dr. Roman Gomez from Southwestern or Southwest Research Institute. He is actually one of the project scientists on one of the instruments for the MMS mission, and he'll be talking more in detail about the things that magnetic multiscale happens to be doing. I said there'd be an obligatory. I said there'd be an obligatory aurora picture. This is actually from Iceland, and the actual photographer is down there. I left his mark up there so you can actually get credit for it. All of the aurora pictures look very cool. They are interactions with neutral atoms in our atmosphere that are being bombarded with energetic particles, and therefore they charge exchange. And then when they charge exchange, you get the different colors. So let's talk about new missions that have just gone up, and this actually just launched last year, Parker Solar Probe. Thanks to my colleague, Dr. Noor Raufai from Johns Hopkins University Applied Physics Lab. He actually sent me some slides of the recent talk that they gave at the American Geophysical Union, detailing the recent findings of Parker. And Parker is designed to help with living with a star, but it's designed specifically as the spacecraft to get the closest we've ever gotten to the sun. And the thing about Parker that makes it interesting, okay, I'm a sports fan, so we'll use a sports analogy for a minute. Imagine the Earth, okay, imagine a football stadium and put the sun at one goal line and put the Earth at the other goal line. Typically, we're observing the sun from far enough away that we're observing it essentially from the other goal line, so we're observing all the way down the field. Parker will travel close enough to the sun to be the equivalent of observing the sun from the opposing 3-yard line. So we're about 97 yards down the field. And then looking essentially at the... So Parker is essentially a first and goal opportunity to learn more stuff about the sun. And one of the reasons that we care, of course, if you notice on the video at the bottom, you'll notice as the video plays, more and more lights go out. These are results of an electrical storm or a geomagnetic storm in the 1980s that actually caused most of the eastern seaboard to have a blackout due to solar energetic particles. This one takes a while. This one's the one that takes a while to load, so we may end up skipping it. But I'll talk about it, but I don't know that it's going to load fast enough. But what that video is, if it loads all the way, is it shows an animation essentially of Parker using using gravity assist from Venus and from Mercury to get itself back into its appropriate orbits. And you watch it as it goes through. Every time it passes by the sun, it gets closer. And it's designed, we sent it up last year near solar minimum to give it essentially 5 years to get into its closest approach right for solar maximum in 2023. And so we watch it and it circles through. And right now these are sort of the future orbits, and we're using gravity assist from the various planets to get closer and closer to the sun as it goes in. Parker will observe the sun its main mission extends through summer of 2023. And it observes the sun with 4 different suites of instruments. And I'll talk about each one as we talk about specific results that it has. Pop through here. And so the idea of the Parker mission, you can see an entire solar. This is an example of an entire solar cycle in X-rays. This is actually a copy from Yoko, which was one of the early X-ray satellites. But we launched it during solar minimum. By the time it ends its prime mission, we'll be right in the middle of solar maximum, and it will be right there on the sun's doorstep, looking at all the things as they explode. So one of the things that comes up as you look, one of the instruments that Parker has is a wide field imager called WSPR. It's wide field imager for solar probe, but we always try to come up with acronyms, and then we can't actually spell things, so we make them sound like actual words, so we don't sound too goofy talking about them. But what WSPR does is it looks wide field from where Parker is and looks out both in toward the sun and then out away from the sun as we get further and further away. And we look at the solar wind, and we've looked at the solar wind, and the solar wind is a relatively constant barrage of particles that's always coming off the sun, although it comes at different speeds depending on if there's an event going on or not. But within the solar wind, we actually see turbulence, and we see different shapes, and we actually see these magnetic islands, which are concentrated areas of energetic particles. We've predicted for years that those things should happen. We just haven't been able to see them because by the time we look at the solar wind from here at Earth, it's had 93 million miles to straighten out all of the turbulence. So by the time it gets to us, it looks like it's behaving fairly normally. But when it's nearby the sun, it doesn't appear to be, because you're looking at the different magnetic islands that show up, and these magnetic islands are places within the solar wind that are more energetic than others. That was one of the key discoveries that was released to the public in November of last year and then talked about at AGU in December. Another interesting one was actually proposed back in 1929 by Henry Norris Russell, who anybody that's had my astronomy class or has had an astronomy class or is an amateur astronomer will be familiar with the HR diagram. That's the same Russell as in the HR diagram. Our star and the stars like it should have a dust-free zone, because there should be a point where you get close enough to the sun that essentially none of the dust can exist because it all gets vaporized. We haven't been close enough to actually observe it yet until now. And so WSPR is also seeing the first evidence of the dust-free zone among its various observations. It basically shows that the dust level it gets fairly consistent all the way till you get close enough in, and then it just drops off because all of it's been vaporized. One of the other instrument suites is an instrument suite called ESIS, which is actually looking to do a more integrated science study of the sun, but it's also looking during quiet times right now because we aren't near solar maximum. And we're seeing sort of energetic particle events that are smaller in nature than the ones that we normally see, but they're still evident as the same types of flares and CMEs that we normally see during solar max. But they're small enough that if we watch them from our in situ measurements, when we make particle measurements in situ, we're not seeing them because they've basically been reduced to noise. There's not enough intensity that it shows up as an actual signal. It just basically shows up as background noise unless you're close enough in and you can see them. So that's what ESIS is actually showing us at the moment. And so these are evidence of that. We've got 1 hour averages, and we see the spikes in these are ion time of flight, and you're looking at the total counts that are for particular ions, and you're seeing spikes that are consistent with an energetic particle event, but the numbers are small enough that by the time they get to Earth, those things have been flattened out to where there's no, to where we're not going to necessarily see it when we look at our Earth data. Two of the other instruments are an instrument called FIELDS, which looks at electric fields and looks at magnetic fields, and then SWEEP, which looks at solar wind, electrons, alpha particles, and protons. Again, we come up with creative names. And we actually found that there was unexpected magnetic structure within the solar wind. And we'll see if this video wants to load, but you'll notice as the beams from the solar wind essentially shoot out, you'll notice as they're close to the sun, you see these very quick little, they actually title them switchbacks because they're kind of like switchbacks for trails where you go all the way down and then you turn around really quickly to go one way and then you turn back around and go the other way. Those switchbacks are actually believed to bring some of the energetic particles back into the corona, which can help explain that coronal heating issue that we've talked about before. If we have all these accelerated particles and now they're streaming back into the corona, they're extremely hot compared to the rest of the coronal plasma, and they can heat them up on the way. Went too far. Another mission, this is actually a mission that's coming out in 2023. It's a mission called PUNCH. It's called the Polarimeter to Unify the Corona and the Heliosphere. I like the name PUNCH better, so I'm going to call it that. This is actually from Dr. Craig DeForest and Dr. Nicolene Weil, and also Dr. Sarah Gibson from SWERI, Goddard, and HAO, the High Altitude Observatory. And this is a small Explorer satellite that is supposed to be launched in 2023 that will actually look to fill in the gaps from, we have observations of the sun at the sun, and we have some observations of particles at Earth, but we have that 93 million mile gap that I talked about before. And what PUNCH will do, will use polarized light to actually get more of an in-depth picture of what the solar wind and what those particles look like as they're coming toward us, but before they get here. And so what we're looking for with PUNCH is to look at solar physics, which looks at how is everything behaving at the sun, and heliophysics, which basically looks at how is everything the sun is doing reflecting in interplanetary space. And we're looking to merge those two so we get a more complete picture of the story. And so its driver is that we want to understand how the corona gives rise to the heliosphere and the solar wind. We're going to do direct continuous 3D imaging because we have 4 different satellites and we can triangulate things to get 3D images when we do image processing. Measure polarized images of Thomson scattered light every 4 minutes. And we have 4 synchronous small sats that are at 570 kilometer sun-synced low Earth orbit. It's a 2-year duration of a mission, launching in early 2023. They're doing their preliminary design right now. They're also looking at doing outreach and doing student-related projects along with it. And I've already been in touch with Dr. DeForest and Dr. Weil about potentially having projects that we can tie in, either doing outreach stuff with them or doing possibly student-related science that may be occurring here at SWOCC. So we try to take advantage of the fact that we know that these things are coming and try to get your students in this community and community members as a whole of this community an opportunity to participate in science like this. And with that, leave the one last thing. This is the actual mission of Punch, looking at the different things. We're going to look mostly for solar wind microstructures in turbulence. We'll also look at how does the solar wind evolve, and then we'll look some at CME trajectory, structure, and evolution. So we'll get more details on what the CMEs look like before they leave, and then afterwards as they're traveling outward. I do want to acknowledge various people that make this talk possible. I will give special thanks to Dr. Nora Ralphie and Dr. Alita Higginson from Johns Hopkins Applied Physics Lab, Dr. Nicolene Vial-Kepko from Goddard, Dr. Craig DeForest from Southwest Research Institute Boulder campus. Some of the images are actually from the OpenStax Astronomy textbook that I use in class. The Solar System Ambassador Program, I'll give special thanks to Kay Ferrari and Heather Doyle that are the program managers at Caltech and JPL. And I will, of course, thank each and every one of you for attending, and thank Dallas and the IT department for making this work, and my students and my friends within the physics and engineering department, that if it wasn't for certain people like Crystal, like Wade, and like the students that are here, we probably wouldn't be having these events. And so I'm very glad that these things happen, and I feel like everybody should get acknowledged. And honestly, all of you deserve a round of applause for being here. And with that, I'll be quiet, and I'll turn things back over to Crystal, and she'll wrap up and tell you a little bit more about stuff that we're doing in the department, and then we'll open things up for Q&A, and you guys can play Stump the Astrophysicist.
I don't know where it's at either. Hello. We're looking for the microphone for the Q&A. Basically, I just wanted to let everybody know we have a lot of really neat things happening here at SWOCC, and sometimes not everybody knows what's going on. So we try our best to get it out there in the media, not just with social media, but with the newspaper, the news, radio. But still, we don't reach everybody. So we like to take opportunities like this to where we can let you know we've got some really neat things going on. We've got the Oregon NASA Space Grant Consortium, which has helped. They provided us with balloons for our SPEAR team, which is our atmospheric research team. They had provided the software for one of the or more than one of the SCORE students to do solar physics research. The SCORE students actually go up to Corvallis at Oregon State each year to present their research. They also are presented a check for along with that, which is pretty neat. But it's some real life hands-on experience for these students. And we also have Invent Oregon, which is another really neat program going on. And we've got 2 teams this year that's going to be competing in that. Last year, our team made it to the semifinal. So actually, they went on to the finals up at Portland State. And so we're pretty excited about that again. We will have a showcase here where everybody can come and see what they have came up as an invention, and then they will go on to Portland State, and then from there they can compete for able to receive checks to be able to continue their work. And again, it's just an amazing opportunities happening right here in Coos County. We're quite lucky to have somebody like Dr. Coiner here in this area. We was trying to think of what else we've got to talk about. If you didn't get a chance to see the Remembering Apollo exhibit, we're actually going to be taking part of that with us to we were asked to come bring it to the annual NASA Space Grant meeting, so they're going to get to do that. This year we're going to be putting together an exhibit to celebrate 30 years with the Hubble. We'll be asking this is the part that I'm excited about, because not only am I passionate about science, but I also am an art history student myself, and I like to create exhibits that get everybody excited about what we're trying to teach and allow students to learn it while they're creating these pieces to be displayed in the exhibit. And that could be a variety of different types of things, whether it's coming from a writing student or an art student, a science student. I'd like to get welding, the welding students would like to get history students, because everybody has a different perspective on what exactly we're learning about, and they have different views, whether it's a positive or a negative view. Everybody has their own opinion, their own way of looking at things. We should look at all the different ways of looking at things and learn about all of the different positive and negative. And if you're looking at it from this way or that way, it's still, we're not saying it's right or wrong. It's just about learning about it. So I'm excited about that type of thing. And this year we're going to be doing that on 30 years for Hubble. And so that is going to be on display in Eden Hall in the gallery this summer, because we also have, if the community, anybody wants to get involved with it, we'll, definitely make room. It's exciting. Yeah, just reach out. So we're fixing to start the Q&A. My son Wade's actually going to help with. He likes to, if you hold up your hand, he'll bring you the microphone, and you can ask any questions, and we'll try to do our best to get to as many as we can. So thank you again.
Hello. Oh, there it was. Here you go.
Hello. Yeah, I was noticing, I've been keeping an eye on the cycles and everything. Have you noticed a 7-year cycle that they go through? And I'm only saying this because we're leading into the 25th, and it falls in line. I believe it was solar cycle.
25 is the one that's coming up.
Yeah, but November 11th, 1958, when it came down and we could see the Aurora Borealis all the way down to the 40-degree.
Yeah, I know.
Do you anticipate something like this in 25, since it's falling right along with that?
It is possible. It is possible when we get closer to solar max that we can have days like that. There have been instances where on certain events, what's known as the Carrington event, which happened in 1859, actually created auroras to go all the way down to actually Florida. So if you get a large enough event, you can stretch the auroras all the way down to the southeastern United States. Typically they're more in the northern portions of Florida and the northern portions of the United States and the northern portions of the world as a whole. But if you get a strong enough event, I came to Oregon from Oklahoma. There were a couple of days that we had strong enough events that you could actually see the aurora in Tulsa, Oklahoma, but that was twice during my lifetime. So it's not a very common occurrence, but it is possible depending on the level of geomagnetic storm that we're seeing during solar max.
Thank you.
Dr. Coiner, from a mechanical engineering side, what did they have to do to the Parker probe to allow it to be able to function so close to the sun without it being affected by these energized or excited particles?
A lot of it had to do with specific types of heat shielding, and I'm not going to pretend to actually know all the details, but I know a lot of it actually had to do with using a lot of specialized water cooling, that they would actually use water to, the water would boil off before it could actually interfere with any of the hardware. Now, specifically how that works, I'm going to defer to the team itself, and I'm not going to pretend to understand from an engineering perspective exactly how it works, but that's what I understand anyway.
Fascinating. Thank you very much.
No problem.
Who is next? You. Okay, here you go.
Back on the Parker probe also, what is the time frame in that slingshot?
The time frame in the slingshot, that entire slingshot goes through the entire 4 to 5 year mission of Parker, and it goes through the 7 passes through the sun. So when it goes through a slingshot about once every 6 to 9 months during that, and gets redirected in the direction it needs to go.
Oh, 1 second. Here you go.
So we're learning all this information about how CMEs interact with our technology. What kinds of things can we do to protect, let's say, the energy grid, the electricity grid?
A lot of what we do in terms of the energy from CMEs, a lot of it has to do with shielding of circuits. There are ways to electrically shield things so that those types of bit flips cannot occur. A lot of times with satellites, we also do things with double and triple. We may have multiple systems that do the same thing, so in case we have one that's interacted with a bit flip, you still have backup systems that are unaffected, because bit flips are fairly random, so you won't necessarily, the likelihood of you hitting the exact spot on the circuit in all three systems at the same time is not very likely, but you may lose one. So you have essentially multiple backup systems. And then as far as for the astronaut health and well-being, we get an idea based on, there's actually a part of NOAA right now, which is called the Space Weather Prediction Center, that looks at the information from the GOES satellites that have X-ray detectors pointed at the sun, and they're looking for signs of solar flare activity. And usually if you get a solar flare, you can plan for about a day and a half out as to when that flare is going to interact with the Earth's atmosphere. And so they're able to sort of schedule activities around so that they're within the shielding of the spacecraft or within the shielding of the ISS before the event actually goes through.
Do you have one more? Yeah. Okay. Here you go.
When will we be able to see images from the satellite?
Images
the
from
public.
Parker, the stuff from Parker, we're actually seeing, when I showed you the solar wind image with the magnetic islands, those were actually images from the wide field, from the WHISPER device. In terms of actual photographic images, there aren't really any on the Parker mission, but we're launching, both ESA and NASA combined are launching a new orbiter that actually is scheduled to launch on February 5th, so just in a couple of weeks, called the Solar Orbiter. And it will actually be taking full disk images that will sort of complement the images that are taken by Parker and give us more of a full-scale observation of what's going on.
Yeah, because I enjoy watching the SOHO images that come streaming through, and I just wondering if this was going to do the same thing.
It'll be similar. SOHO and SDO right now still take images. SDO takes images every 10 seconds, 24 hours a day. Creates about a terabyte worth of data every single day. I'm glad I'm not in charge of the computer
Thank you.
system to hold it, but it's all there.
I have a question.
Okay.
Okay.
I guess if we're going to let you be microphone kid, you get to ask a question.
Okay. I actually had a question. We know in like probably millions of years that the sun is eventually going to blow up and stuff. Very technical term. Is there any way we could move to another planet with a new sun or star?
Not at this point. And I say that, and it's not likely to happen at all, because the closest star to us, if we were to move to another star, the closest star to us is 4.2 light years away. So if we could travel at the speed of light, it would still take us 4.2 years to get there. And we can't travel at the speed of light, so it would take even longer. So it's not likely that we would be able to do that. There are faster engines being developed. It's not, because of relativity, it's not possible to travel faster than the speed of light if you have any particular mass. So if we're trying to relocate an entire society, it would take several generations of people just to make that trip, and lots of fuel that we don't necessarily have. But I wouldn't worry about it too much, though, because the sun has a good 4.5 billion years worth of life before the potential of a red giant stage and a nova stage come in. So most of us, unless we Futurama ourselves, will not be here.
Thank you. Does anybody else? Oh, here.
Now, I just read an article last year. Now, it stated that some stars nova more than once.
Some of them do, actually. It depends on.
Now, could ours?
Ours won't because of the mass limit of the star. Ours barely has enough mass to actually get to where it can fuse carbon, which is the first time it'll go nova when it fuses helium, and then if it actually got to the point where it fused carbon, it would go nova again, but it can't. Our star is not massive enough to actually fuse carbon. So the only nova that we'll see is when it switches from hydrogen to helium.
Thank you.
But in larger stars, like in recent weeks, there's been a lot of discussion about Betelgeuse, the star in the shoulder of Orion that's going dimmer than we expect. It's a red supergiant star, so it's gone through any number of those flashes, and we're kind of anticipating at some point that it's going to go supernova because it should be somewhere near fusing iron, and when it hits fusing iron, then that all stops. And so it keeps doing these flashes until such time as it runs into fusing iron, and then it can't fuse anything anymore, and gravity eventually collapses it all down.
What about all the top view? Now that one just flared up.
That one flares up as a nova, and these things do happen. Yeah. There are large black holes in the center of all the galaxies that can sometimes cause flares if they're starting to pull on other objects. It wouldn't be in our case because our location in the galaxy, we are very much in the suburbs of the galaxy, so we are out on the outer edges, and we wouldn't necessarily be anywhere near the event horizon. I didn't hear that one, actually. Yep. Right. That is in our Milky Way galaxy. That's looking back toward the center. So you are getting closer to the center. You're not quite there yet, but you're getting close enough that could be affected, but wouldn't necessarily affect us all the way out here.
So, with all this funding and discovery and time and intelligence, how can this technology save our planet from what's happening now? What can we do? What is the application of all this time, work, money, energy, intelligence?
Well, that depends on what you want to consider an application. I personally, the reason I look at it the way I do, the sun is going to behave how the sun chooses to behave, and we are kind of stuck in a situation where we are pretty much powerless to do anything should it decide to throw things at us. But it would be nice to know that those things are coming and to be at least prepared for them. So in order to understand when are these solar flares going to come in, how can we expect, what kind of emission, what kind of radiation can we expect? Can we expect these types of ground level events that cause power outages? We need to know more information about how the sun is behaving in order to be able to predict those things. Once we get to the fact of knowing how to more specifically predict the events, then we can work on solutions to sort of mitigate the problems that can be caused by them. But right now we're still, even though we've got all the observations we do, there's still a lot of unanswered physics questions that we don't necessarily know how the sun is necessarily behaving as far as all of this is going. So we have to understand what it's doing before we can make contingency plans on how to live with it. I will once again thank you all for coming, and I'll be happy to talk to any of you outside if you'd like to continue the discussion. But for now, I'm going to take a breath.